Good afternoon, everybody. We welcome you to this live interaction session for this NPTEL course, Trace and Ultra Trace Analysis of Metal Ions using Atomic Absorption Spectrophotometry. This session is intended for students and people who are going to attempt the exam. And if you have faced any concerns during the course of the NPTEL course with respect to assignments and any questions you would like to clarify directly, this is a unique and a wonderful opportunity for you to interact live with Professor and get your questions clarified. Professor will give you a brief introduction about the course now, and then we will take up some questions from questions later on. Sir, over to you.
Welcome, students. It is a pleasure to meet you all. NPTEL has given us an opportunity to interact with you regarding this course on atomic absorption spectrometry for pollution monitoring. I have been thinking about the metal analysis using atomic absorption because it is one of the most important techniques to monitor the toxic metal ions in the environment. Basically, whatever you say and do, the idea is if anything is in excess, it is dangerous in the environment to the people also and other animals, plants, etc., etc. So the only technique we know about atomic absorption, about the determination of the metal, is atomic absorption, because it is a specific technique. That means if the metal element is there, it will show you positive result. If it is not there, it will fail the test. If you look at some other techniques like spectrophotometry, for example, you have to react with colorimetric reagent, and it will show you some colored substance, compound formation, but it will not be specific because many other metals may be reacting in a similar way, or they may be reacting to give you products of different colors. So there is no sure way, absolute sure way of determining a particular element if it is there in the environment or not. That is why atomic absorption has taken a most important role in our day-to-day life. If you want to make sure, 100% sure, that an element is there in the effluent or in a food or in a medicine or in any other air or any other matrix, the only sure short way to determine the metal, if it is there quantitatively, is atomic absorption. Nowadays, there is another possibility of looking at the element using ICP AES also. That is also comparable. But atomic absorption scores over the ICP in the with the fact that you can actually determine the mass concentration of the element present in the effluent or in the matrix. So that is where the atomic absorption is relative technique. ICP is also relative technique, but atomic absorption is the absolute relative technique. In the sense, the element is there, it will show you yes or no, pass or fail. And if it is there, it becomes relative to determine how much of the material is there in the sample. For example, what we define in atomic absorption is characteristic mass. That is the signal corresponding to 0.0044 atomic absorption. If the element is there, it is above the three times noise of the instrument, you are 100% sure that the metal is there. Okay. Now the beauty of this absolute technique is it permits you to determine the elements in microgram level, sub-microgram level, nanogram level, and picogram level. And some of the techniques that I have described to you in this course permit you to determine elements in parts per trillion quantitatively. And that is the beauty of atomic absorption. Now, I will not go more into details regarding the course, because all of you have almost undergone the full course. But I would like to give you a small chart of what we have done in the course. First of all, what we have done is understanding the structure of the atom. I have spent about almost 5 to 6 sessions with you, explaining the structure of the atom, protons, neutrons, periodic table, etc., etc. And then we have spent some time understanding the interaction of electromagnetic radiation with matter. Matter means, in this case, in this course, it is the elements. Okay, elements in the native form. So what are the elements in the native form? They are protons, neutrons, electrons, etc. And in atomic absorption, we are dealing with the interaction of electromagnetic radiation with the electrons. Okay, so the energy of excitation is normally characteristic of the element, and because it is so characteristic, it becomes specific for the determination of the metal. And then what we have done is we have spent some time regarding the instrumentation of atomic absorption. I had taught you about hollow cathode lamps, electrode-less discharge lamps, and the vapor lamps and other things. And then we have discussed about the optics. We have discussed about the flame and non-flame, flame characteristics, and signal handling that we have discussed. And at the same time, we have also discussed about the applications of atomic absorption, spectrometry to different substances in the matrix. Now, apart from this, when you buy an atomic absorption, you are also capable of conducting a similar modified technique using the same atomic absorption instrument. And I have taught you about those techniques. One of them is the flame emission spectrometry, which we have discussed earlier in the course. And that is for the determination of sodium, potassium, cesium, etc., etc. They are the alkali and alkaline earth metal. That is emission. So what is so great about atomic emission in atomic absorption, you may ask? Now the point is, when the energy of the excitation is so low, then with the just change of a button, you can convert atomic absorption into atomic emission. Unfortunately, except alkali and alkaline earth metals, this kind of emission does not take place for other elements. There is a theoretical basis also, which I have already discussed and derived some amount of quantitative expressions for other elements regarding their concentration in the ground state as the atoms. And that is why atomic absorption will have an attachment for atomic emission for sodium, potassium, etc. Then we have discussed another great technique, that is hydride generation atomic absorption, where we convert arsenic, antimony, bismuth, lead, and germanium, selenium, etc., which form hydrides in the reducing atmosphere. And we take the hydride, that is a gaseous form of the hydrides of these 6 elements, into the flame or into the furnace, where we convert the gas into, we decompose the gas into metal and hydrogen. So again, we have a metal at the excited ground state, even around 1000 degrees centigrade. You don't need 2000 to 300, 2500 degrees centigrade to convert the atom into a significant quantity. So very small quantities can be converted quantitatively into atomic absorption by using hydride generation technique, which we have spent a lot of time. And I hope you all understood the fundamental principles and instrumentation, etc. We have done all that. Then we have also spent some time regarding the flameless atomic absorption. I have taught you about the Massman technique and the other electrothermal technique. And here we use the argon gas as a neutral material to convert the sample in a reducing atmosphere again using a carbon tube, which is pyrolytically coated. And these pyrolytically coated graphite tubes permit you to determine 10 raised to minus 12 to 10 raised to minus 15 grams of the substance. That is, you are almost nearing the Avogadro's definition, that is 10 raised to minus 23. 10 raised to minus 15 is a great advance in the determination of these metals, and that is what we have done using graphite furnace, and then we have looked at other applications, etc. This is what I have taught you. I hope you have all learned it well, because it is part of your BSc, MSc, analytical science and organic and inorganic sciences, etc. Someday or the other, if you continue in your profession as chemist down the line, atomic absorption is the one which will stand you in good state. So with these remarks, we will go ahead into looking at some of the questions you people have asked over a period of time, and then I will indicate to you how we can solve those problems. In case you have any other questions, very free to ask me, or my technical assistant, Dr. Rajiv Muskavi, is here, and here is Sarvesh, and both of them are quite capable of answering your questions. You can also ask us later on, if not now. Please convey this to your friends and colleagues, that you can always contact me, because I am your teacher. A relationship between a teacher and taught is entirely different. We don't have to interact only during teaching sessions. So I hope many of you have my email address. You can contact me anytime. You also have my mobile number, I believe. And if you have any questions, you can ask me any day until night 11 o'clock. Okay, thank you very much. We will continue our discussion. I would like to know how many of you have joined now recently during this session. Rajiv?
Thank you, Professor, for the wonderful introduction about the topic. And we have, in a very short summary, we have basically covered the entire spectrum of AAS in the parlance of electromagnetics. I have some questions which were asked by students earlier, but before we go on to that, if there are any questions from the people who have joined here, Soumya and everybody, you can. We will give you the first preference here. Also, you can ask the questions on YouTube as well. So since it's going live on YouTube as well, questions anywhere are monitored right now.
Hello, good afternoon, sir. This is Soumya from KPR IIT Coimbatore, Tamil Nadu.
Yes, Soumya.
How many assignments are going to be considered for this Sir, average number of assignments.
1 minute.
I'm sorry, we did not.
For final certification, how many assignments are going to be considered?
I believe it is going to be 60% of your assignments which need to be taken up. But I will get back to you on this, Samya. If you just put a query across in the forum.
You pass on the
And-
query in the forum,
we got
Soumya.
this one. You can also ask this question in the forum, and we'll
So
reconfirm and then
yes.
get back to you on that question.
So that
And for the final exam on coming Sunday,
Yeah.
we'll be having descriptive questions also, sir, or objective and
Yeah, all the questions which are going to be scheduled on Sunday are objective, and some of them, just like your assignments, how they are scheduled. Some of them are answers, and some of them are quantitative, which needs to be solved. We will be taking some of those quantitative questions which were asked in the assignments to discuss now, some of them at least, and some more questions from other students.
thank you,
Is there
sir.
some
Thank you,
questions?
sir. Professor, we had a great experience with your talks and all. I'm thankful to you, sir. Thank you, sir.
Thank you, Soumya. Very nice of you.
So moving on to looking at some of the problems which we'll cover today. Let me just go to the screen share. So the first question, which probably could be answered, is determination of the energy of a photon, where the wavelength of the photon is given. So in this case, the question is, what is the energy of a 430 nanometer photon in the visible radiation?
430 nanometer photon energy.
Yeah, that's right, sir. So
The solution is very simple. If you have understood the introductory part of the course, now you will all remember this equation, that is E is equal to Hc by lambda, where H is the Planck's constant. I am not going to write to you the numbers of Planck's constant here, but if you know, these are all these data is available. H is Planck's constant, C is the velocity of light, and lambda is
the wavelength to be
the
determined.
wavelength of the radiation. Only thing you should remember when you want to convert all these things is to remember the units. Now, what are the units of H? The units of H is joules second.
Just to mention here, these units of the constants which are to be used in the questions, they will be provided to you. You just have to be a little careful about the units and the exponentials.
Okay, and the C is 3 into 10 raised to 8 meters per second. Quite often, a lot of people remember 3 into 10 raised to 10 centimeters. Okay, now there is something you should remember, that this is 430 nanometers. So we should be consistent with the use of meters. That is why I have written here C is equal to 3 into 10 raised to 8 meters per second. And obviously, you also have to convert this 430 nanometers into meters, isn't it? So lambda is equal to 430 into 10 raised to minus 9 meters. If you put all these things, see, you will get the answer. That will be approximately, that will be 4.6 255 into 10 raised to minus, well, I'll write it here because there is a 10 raised to minus 19 joules. Okay, this is the answer.
So
Okay.
in a typical question, you will in your exams, the format will be similar. You will be given 4 options of the numbers, and you will have to pick up the right option out of them. You need to solve the problem and then pick up the right option.
You also have to remember the units. Okay.
Units.
Without units, you will end up mixing the answer, and the answer will not be correct. For example, if you just use 430 as lambda, definitely you will end up with some funny number here, because here what you should be using is in meters now, and here also it should be in meters. There only all other units will either get cancelled or something like that. Okay, here there is seconds and here there is seconds, so they will get cancelled. So all other units will be in consonance with the requirement of the answer. This is what I will be expecting from you in the examination. I may give you, instead of 430 nanometers, I may give you 400, 4,300 angstrom units. Okay. So obviously you will have to remember the conversion of angstrom units to nanometers. Actually it is 430. Okay. So small changes we will be making just to make you feel comfortable with the unit. Okay. Can we move on to next one?
Yeah, we'll go to the next question, sir. I hope that has been taken down, and I don't see any questions in the chat box, so we can go to the next screen. Next question.
Just give us 1 or 2 minutes. We'll be sorting out.
It's okay, sir. So I think the next question is also on the similar. Only thing is here the question is asked in the inverse way. The frequency is given and the energy is to be asked. I think we'll take up the other question, sir. So here there's a question which comes from the week 5 assignment, which is a problem. The determination of manganese at 403.3 nanometers. Solution A of unknown manganese concentration gives a reading of 45.
Okay.
Solution A.
Unknown manganese solution.
Yeah. Gives a reading of 45. Solution B, having the same concentration as solution A, plus 100 microgram per ml of spiked manganese, okay, gives a reading of 83.5.
Solution B gives you 83.
Yeah, solution B is solution A plus 83.5. Solution B is basically solution A plus 100 microgram per ml.
Okay.
So we are asking you, what is the concentration or the quantity of manganese in solution A?
This is A, right?
That's right. So it's a straightforward question. If we assume my A as X gives you a reading of 43. That is X plus 100 gives you 83.5.
$83.5 to solve for X. Okay.
X gives you how much? So it's basically cross multiplication.
Right? So if you 83.5X, no?
Yeah.
So here it is 45X.
X is 45, sir.
X is 45. So it is 45x. So you can always calculate x is equal to, you just write it like this, 4,500 divided by 38.5. You just solve for x, and that will work out to approximately 116.88 microgram per milliliter. It is a high school chemistry. All you got to do is understand the units instead of getting confused with the wordings. There is nothing much involved in this. Okay, it is just almost all analytical scientists face such problems. And it is not that they cannot solve it. They solve it, but they have to understand what is the dilution factor, what is the original, what is the solution. It's not even, it is all, we teach this kind of mathematics for the 5th standard. Okay, next.
Another question which is
wipe off.
Yeah, another, I hope this is taken care of. Another question which is of common understanding is the question of the resolving power of a monochromator. Okay, so the question here also comes from the 5th assignment. Okay, the question here says estimate the theoretical minimum size of the diffraction grating that would provide a profile of the atomic absorption line at 500 nanometers having a slit width of 0.02 mm. The diffraction is of first order.
I think it goes right.
Yeah, you can write.
So
resolving, resolving power, you can just
nanometer.
It's lambda by delta lambda. And the line width is 0.002 nanometers.
That is, why do we say line width 0.002? Because this is the minimum broadening of the wavelength corresponding to Doppler effect and the ion effect, van der Waals effect, Stark effect, and other effects. So we are looking for, this is the maximum broadening. Now, you should remember this. Please refer to the text when I was teaching. So the formula, what you should be using is nothing but a resolving power is equal to, what is that?
Lambda by delta lambda.
Lambda by delta lambda.
That is the line width. So it's 500.
Okay. This I have taught you in the 2nd chapter, that is interaction of electromagnetic radiation regarding the prisms, interaction of radiation with prisms.
That works out to be 2.5 into 10
So
power 5.
all you got to do is divide 500, that is lambda, divided by 0.002. So very simple. 002. Now all units are same, right? So nanometer. So never forget to use the units. So this will work out approximately
2.5 into
2.5 into 10 raised to 5 grooves. So where n is the
the second part of the question here is the assumption that the grating is of first order and it has to be ruled at 3600 grooves per mm. So the grating is the first order diffraction is what has been asked, and the grooves are ruled at 3600 grooves per mm. So the size of the grating is now given by 2.5 into 10 power 5 grooves divided by 3600.
So very simple. All you got to do is divide this by this.
And you get the answer as
you get
69.
The answer, something like 69.44. We have already solved it. So You don't have to worry about the accuracy, but I want you to concentrate on the units. That is, otherwise there is nothing there. That means the grating needs to be ruled at 69.44 millimeters distance. So it is something like a shell grating. It's not an ordinary grating, because in ordinary grating you will be ending up with about 3,000, 1,800, 1,200 grooves, whereas in a shell grating 69, 80, 100, 150 grooves are expected. Okay. So that is the beauty of a shell grating. Okay, that I wanted to bring home to you the importance of shell gratings in all modern instruments. That is why this question was chosen. Any other problem?
Yes, one of the another very common problem and an important problem is the ratio of the excited and the unexcited atoms. Okay, that is the ratio of the ground state and the excited state of the particular atoms. And this question has been asked in week 6 as an assignment problem also. Yeah. Right, and the equation to be used is Professor is going to explain to you, and that is, if you solve for the equation, you should probably get the answer here. And the question is, the ratio of excited potassium atom to the ground state is 4.58 into 10 power minus 4.
1 minute. Please read slowly.
Okay.
I can write it for them.
Okay. The ratio of excited potassium atom.
Potassium atom.
Ratio. It's a ratio.
Yeah.
Excited atoms to ground state is 4.58.
4.58
into 10 power minus 4.
Into 10 to the power of minus 4. So potassium atom ratio. That is ratio of potassium metal.
That is Nj by N0.
That is excited divided by unexcited. Correct?
That's right.
So this is equal to 4.58.
Probably if you could write the equation first and then.
That I will write it now. First you must understand that the ratio, that means, what does it mean? This means that only 4.58 number of atoms are excited out of 10 raised to 4. That is, out of 10,000 atoms, only 4 atoms are excited. So this is a very small number, but again, this brings us to the point that atomic emission, even though it is so less, the concentration of the atoms in the excited state, even though it is less, still it can be determined using atomic emission. Now, this I had taught you while teaching you the atomic absorption theory. The basic idea was you must have the number of atoms in the ground state from which the electrons can get excited, atoms can get excited to next higher energy level. So for many other atoms, like let us say zinc or cadmium or magnesium, this will be of the order of something like 10 raised to minus 12 to 10 raised to minus 15. Okay, it will be in this range. So the atomic absorption works out for this, whereas for this, atomic emission will work. Now, the ratio of the excited atoms to the ground state is given by Nj by N0, that is Boltzmann distribution constant. What is that?
Nj by N0 is
Nj by N0
is equal to
Gi
and by G0. That is the statistical weight for the 3s and the 3p state.
Correct. Statistical weight for 3s and 3p state. This data you will not be getting it from the textbook or something like that, where to give you. But such data is available. but only for the explanation, for the sake of I do not want you to derive this factor, this GI. Okay, then we
E to
have
the
the
power of
exponential of e to the minus Ej by kt. Okay. Now Ej is the
Excitation
energy
energy.
for excitation. K is the Boltzmann constant,
and
and
T
T is the temperature in absolute Kelvin. Okay. Don't write T as if I give you degree centigrade, don't use it as centigrade. You have to convert it into
Kelvin.
Kelvin.
Because Boltzmann constant is given in Kelvin.
Yes. Boltzmann constant also has got units in Kelvin.
So if you solve for this particular equation where you know the Nj by N naught and Gi by G naught, and the excitation energy is given to you, that is 2.59 into 10 power of minus 19. All you have to do is solve for T.
Now I'm going to write 4.58, that is Nj by N0 into 10 to the power of minus 4 is equal to
6 by 2.
6. What is that?
That is a statistical state. Gi by G naught.
3.
Yeah.
That is 3. Gi by G0 is 3. I have explained to you while explaining this that for most of the elements it will be approximately 2.2 to 3 range. That is the statistical weight of the excited and unexcited atom. Then other things become very simple.
E to the power of
That is 3 into exponential. Okay. E to the power of.
minus 2.5.
Now we write minus Ej. That is what is Ej given in the example?
2.59
This data is given to you. 2.56
into 10 power of minus 9.
into 10 to the power of minus 19. It's not 56. It is
59
59
divided
divided by
the Boltzmann constant.
Boltzmann constant. This, but
It's
I
given
do not expect you to remember. Okay, so I have given you this data. In the exam also, if we ask you, we will give you this data. 1.38 into 10 raised to minus 3,
minus 23
minus 23
joules per Kelvin.
joules per Kelvin. Per Kelvin, we write it as minus 1
Into
multiplied by
absolute
temperature. T, absolute temperature. So all other things are given here except T, and you have to solve. That would be approximately 2135.89
Kelvin.
Kelvin. So that is the temperature. Subtract 273, you will get the temperature in degree centigrade. That means,
Explain why this is relevant.
so that means at 2135 degree centigrade Kelvin, I make it minus 273, that will be approximately 1900 degree centigrade. If you spray potassium atom, solution containing potassium chloride into a flame, what you will get is there will be formation of potassium atom, dissociation of potassium chloride or something into potassium atoms and chloride atoms, and the ratio of some of them will get excited, many of them will remain unexcited. Unexcited would be 10,000 and excited will be 4.58 atoms. Okay, this is the beauty of calculation of the ground state to excited atom. That means what, even if you go to 3,000, it may be changing only by an order of about 1. It may come down to minus 3, but for other elements like zinc, cadmium, magnesium, mercury, and many other active elements, it will always be 10 raised to minus 12 to minus 15.
Right. I think these are the questions which that have been asked.
Yeah.
Now we would like to open the floor for any other questions Any other doubts?
If any of you have any other doubts, please feel free to ask me. Soumya? Are you there?
Sir?
Are you there?
Yes, sir. Yes, sir.
Did you understand what we have been talking and writing?
Yes, sir. I have seen your solutions for the problem.
Okay, good. So if there is anything, you please let me know. Okay, there are not many people who have joined because it is a working day,
Yes.
but we will be putting it in YouTube and others can
Yeah.
access that.
Yeah.
So thank you very much. We will close the session unless there is any other question from you.
Fine, sir. Your notes and that book published and all was very helpful. All that consists of these solutions.
You are welcome.
Yeah, thanks.
Okay. So all the best once again.
Thanks.
Bye-bye. We'll meet again. There will be one more session for one more live session. Please inform others that we'll be talking about the assignments from 6 to 10, isn't it?
No, we covered most of the
We
questions.
have covered most of them.
Most of the
So
questions
if
we are
there
able
is
to
a need,
cover.
we will meet again. Okay. So thank you very much and all the best.
Thanks.
Bye-bye.